This is crazy over here. I'm going to hide this. We should be on. Fish on. Why is it 720p? Okay, beautiful. Of course, let me know if you can hear this. We've got more time series streaming to do. So last time we made a time series inputs and outputs work. We built a toy model and make sure predictions work. We evaluated the predictions. Now we're on to replicating time series papers. So let me just tweet this out. Twitch.tv/Mr. D Burke. Is this working? Twitch.tv/Mr. D Burke. Sounds like it is working. Wonderful. I'm going to tweet this out to the Twitters. Hello, Twitter. Going live on... N-beats algorithm. Is that what it's called? N-beats? N-beats. I'm going to share the paper. N-beats archive. We need twitch.tv/Mr. D Burke. Oh, it's so humid here. Twitch.tv/Mr. D Burke. Oh, it's so humid here. Boom. All right, fish on. Shared it to Twitter. And now I'll share it to the Discord. Shivans, what's going on, my friend? I've been really well. So for note taking, I use Bear, this little app here, Bear, and Notion. Yuchi is correct, Bear and Notion. But I just got to share this on the Discord. Yo team, going live on Twitch, writing TensorFlow code for time series data. Come and say hi. Wave. I like that little wave emoji. Okay, beautiful. Yeah, I used to use Trello a lot, but I've just swapped from Trello to Notion. Okay, so we're going to try replicate this algorithm, N-beats. So let's see. This is the version of it. They have a complex version of it, which does a few other things, like we were reading this paper in the last time series, so we'll get to the code in a second. But they have one where you can identify the trend and one where you can identify the seasonality. What we'll just probably focus on is creating a simple version of this one where we just forecast some sort of period ahead using some sort of period in the past. Time series forecasting. Now, do I have my notebook up? Gonna get out of this. Once again, really great video here on why forecasting is a load of crap. So make sure you check out that. Lstm Model, but I'm going to share this again. So I'm going to share this at the start of every time series video, by the way. Hasnain, what's going on, my friend? Good to see you. Hey, thank you for the wave. Okay, so here's our code. By the way, let me know if everyone can hear everything. Leave a thumb up in the chat if you can hear what's going on. And if you can see the screen okay. Gaurav, what's going on, my friend? Who's ready to write some time series code? Rohan, what's good? Thank you all for tuning in. I appreciate it. So we've got some time series data here from the M4 competition. And you can check out the M4 competition here, but basically it's a forecasting competition, M4 competition. Forecasting, remember forecasting is we're trying to predict some value in the future based off values in the past. But M4 competition, it's not a BMW competition, it's M4 forecasting competition. There we go. 100,000 time series data. We're only using one subset of data from the M4 competition because we want to start small first. So as we'll see in a second. Thank you for the thumbs up. Thank you for the shuckers, Yuchi. COVID in Australia is actually not too bad, Gaurav. Let's have a look. Thank you for the kind words, my friend. I hope you're the same. COVID in Australia. Let's see what it says. Yeah, if you see our cases, this is something we could forecast as well. But again, watch this video, why forecasting is a load of crap. But we're still going to be working on it. So, yeah. Oh, 7-day average. They've got that in there. So it is the 12th of May in Australia right now. What's our main focus for today? Build time series models. Yeah, so there we go. We have 8 new cases. Yeah, 8. You heard that right. 8 cases in all of Australia, according to Google. All right, but yeah, here's our time series data. We've got some, it'll be easier to understand this once we plot it. Better, what's going on? Martin, how are you, my friend? Good to see you. Okay, yeah, so this is our time series data, right? You can imagine this as a time series. So this, you could say days, 1,000 days. Oh, this is actually a great example of the turkey problem. So I'll show you one of the problems with forecasting in general, is if we look up the turkey problem, and you should be able to see this. So a turkey, let me zoom in on this. A turkey has a great time while it's living for 1,000 days. However, look at this line. It's very similar to the turkey problem. The turkey's well-being, but we have one value here which destroys the entire turkey. It's Thanksgiving, so the turkey dies here. What would happen if that happened to our time series? We'd have an extremely large, I'm going to increase the fig size here. We'd have an extremely large outlier. Look at this. Compare that to that, similar trend. Not exactly the same, but similar. I wonder if later on in our time series project, as we keep going with this little series that we're doing on Twitch, is we could artificially implement a value here at the final time step that has just a massive drop off and it goes down to like 1,000 or something, and see what happens to our model. We'll probably notice that our model fails pretty bad. But let's keep going. So here's what we want to do. That's the wrong way to make training test splits in time series data. See how the test data is all scattered throughout. We want to go down here. This is the correct way to make training test splits in time series data. In other words, using values from the past to predict the future. And then we can create a window data set, which turns our time series problem into a supervised learning problem. And we're up to here. Right, helper functions. Okay, we need to evaluate preds. I've got a fair bit of code I want to write in this one, so I might not be as active in the chat, so just bear with me. Okay, this is going to evaluate the predictions. So one of the best forecasts you can do, or a baseline you can create for time series data, is naive forecast. So this is our baseline. So a naive forecast is you use the previous time step as a prediction for the next time step. Does that make sense? That's all you do. You use t minus 1 to predict t, where t is your time step. And you'll find that's actually a very hard baseline to beat. And so we've got some evaluation metrics here, which is mean absolute error, mean square error, and mean absolute percentage error. We worked out those in the previous stream. And then if we wanted to create a dense model, we've got it here. Our output layer has no activation function because we want it to predict a number, or we could have activation equals linear. Same thing. And look, see, if we evaluate we just used a dense model. Oh, what did we get wrong here? We just used a deep learning model and it doesn't come close to our naive forecast. This is very important to realize. Model 1 preds. Gaurav says, hey Dan, you made a project on Airbnb, right? Will we be able to replicate that doing the TensorFlow course, or do we have to learn more? No, the TensorFlow course is not focused on that. That was using Detectron 2. So the Airbnb project that I worked on uses Detectron 2. So the TensorFlow course does not cover this. If you want to do the Airbnb project, check out my code on GitHub, as well as the video, as well as Detectron 2. Yuchi, what if we can predict or forecast which regions will be most affected given enough data about the healthcare service and the medical staff available in that particular region and try to save as many lives as possible? Can we do that type of thing with time series forecasting? Okay, so the way I want you to think about time series forecasting, Yuchi, is that think about an open system versus a closed system. So with health systems, it's a very open system. So there's almost too many variables that you can, especially with an airborne virus. This is why all the COVID models are like, show me one that's predicted it accurately without just being luck. Is because in an open system, such as a pandemic, you have too many variables that your model can't predict. So there's too much uncertainty with your predictions. Of course, you can build a forecast, but whether or not that forecast holds water, who knows? Because things can change dramatically. Like you can see this is the turkey problem, right? A turkey has a great life up until Thanksgiving. It has no idea of Thanksgiving. So this is the things that when we're dealing with large-scale open system issues, it makes sense to take the most aggressive option because we can't model all of the variables. Whereas in a closed system, say a computer network or something, you could get a bit better forecast and idea of demand because you control a large number of parameters of that system. So just think about that for forecasting. Open system, lots of uncertainty, very hard to predict. Closed system, still hard to predict, but you have a lot more chance. Now, analogy we all are familiar with is predicting the weather. How many times is a weather forecast wrong? Like, I can look out the window and tell you that it's cloudy versus the forecast from 4 hours ago. Did that say the same thing? I don't know, I didn't check it. But this is my simple forecast, is looking out the window. This afternoon I think it'll be sunny because the sun looks like it's coming out. That's a simple forecast. Whereas a weather forecast takes in data from satellites, from wind farms, I don't know, lots of different parameters, and still can't predict the weather. So that's something to keep in mind. Here's our predictions for our Model 1, but if we zoom in on those predictions, we notice that they're not very good. All right, so there's a naive forecast. Look how close that model. So remember, the naive forecast uses the previous time step, the value at the previous time step, to predict the next time step. So this is our deep learning model versus a naive forecast. So our deep learning model doesn't do very well. And if we find Model 1 results, Model 1 preds, there we go. We find out we get significantly higher than naive results. So almost, almost 3.5 times MAE, 3 times the MAPE, and almost 10x the MSE. So something to keep in mind, right? It's actually going to be very hard for us to beat our naive results, but we're going to try anyway. Hey, Bebe Gunda, welcome from the Zero to Mastery Discord. Thank you for tuning in. Yuchi, I'm glad you like the explanation. Martin says, how would I compare Pytorch with TensorFlow 2.0? So the way I see it, right, is that because a lot of the work in deep learning and machine learning is very open, and a lot of the problems that we have are similar. So both toolkits, Python and TensorFlow, are working towards solving similar problems. So I would say that prior to TensorFlow 2.0, you would probably find Pytorch a lot easier to use. However, since TensorFlow 2.0, a lot of the great things of Pytorch have been integrated in TensorFlow. And I would also say for Pytorch as well, vice versa. So there's a few things that TensorFlow did that Pytorch didn't have. Now they're sort of moving towards being very similar to each other. And what I want, rather than sort of spending so much time deciding which one to use, either one you pick, does it help you solve the problems that you're working on? That's what you should, or a simple one is like, does the team that you're working with, which one do they use, right? But if you know the overall concepts in Pytorch or TensorFlow, so the process of processing data, building a model, evaluating your model's outputs, which are going to be similar no matter what machine learning framework you use, then the only difference is the syntax, so the code itself. But if you know the principles, right, that you're trying to build, you can start to pick up the syntax. I would argue that if you're skilled in TensorFlow, like you have 1 year's experience, you could get that same level of experience with Pytorch in a compressed amount of time, so say like a month or so of diligent study. And same goes for vice versa. If you're experienced in Pytorch, you could get similar level of experience with TensorFlow in about a month or so of upskilling. And now, if it was for just one particular project, it might take you just 2 to 3 days to transfer it from TensorFlow to Pytorch. Again, timelines are arbitrary, but just think of it like that. I have more experience with TensorFlow, hence why I'm using it. Now, okay, so now we've created a window data set. We needed to update it to, I need to put a note here that to do for windowed data sets, if we need to reshape data set size within a model, we can use a lambda layer. So that's TF Kera's layers. Lambda, and it would be lambda something like x, TF expand dims x axis equals 1. Something like this. Okay? And we're going to keep going with this. So this is a convolutional neural network, one-dimensional. We'll see how that goes with our test data set. Model 2 preds, we make some predictions, wonderful. And if we plot the zoom preds, yeah, see again, our convolutional 1D neural network still doesn't beat our naive forecast. What is a naive forecast? It is, again, using time step, the previous time step to predict the next time step. By the way, this is a univariate time series data because we only have one value. We're using the value itself to predict the next step. Multivariate time series is you would have the value itself plus other values built in. I want to get rid of this, model.evaluate, model 2 results. So once again, if we look at model 2 results versus our naive results, we see even a convolutional neural network can't beat our naive model. I'm just going to close this window. Gaurav says, I've seen other data science channel and yours is among the best. Thank you. I appreciate that. I guess if you put out more videos and work on the channel, you'll be at the top. Thank you, Gaurav. Antonio says, is it necessary to normalize the variables to forecast with neural nets? Yes, we could normalize them, but at the moment it's working for the time being. You are the best teacher. I'm complete beginner ML coding in general, following a Udemy course, and have really helped me. Thanks. Oh, thank you for the kind words, Bebe Gunda. I appreciate that. Okay, now we're going to do an Lstm model. But as we'll see, if we fit this, we're not going to spend much time here because I really want to just start building this next model. Get out of this, get out of that. We find that, yeah, our LSTM performs the worst. Look at that. That's terrible. We predict the trend in some way, but it's too high. So, and we really don't have a large data set here. We only have, that's another thing you got to worry about time steps or time series data, is that if you had one variable for the last 10 years, per day that is, you would only have 3,650 variables, whereas we know deep learning models like lots of variables. So now we're up to building a more complex model. So we're going to try to replicate the architecture in the NBeats paper, specifically this one. So let's dig into that, shall we? So we replicated MAPE in code here. Built in. And we're going to get rid of that. And let's write here, building an NBeats block. So they have block, which is 4 times fully connected stack, into stack, which is n blocks, into full architecture, which is m stacks. Okay, so we need to define the block. I think we're gonna have to define a TensorFlow custom layer for this. TensorFlow custom layer. So let's see what this means. Should I move my face to the bottom of the screen? Let's try this. Is that better if I'm down here rather than up the top? Let me know. Custom layers, here we go. So yeah, we recommend using TF-Keras as a high-level API for building neural networks. That said, most TensorFlow APIs are usable with eager execution. So most of the time, the best way to implement your own layer is extending the TF-Keras layer class. So let's do this. Create nbeats layer block. We need to class nbeats block TF. I'll call it a block layer so we know that it's a layer. TF-Keras. All I'm doing is going to copy this and try to assign it to my own problem. TF-Keras layers dot layer. We need to initialize it. Self num outputs. Maybe we want n outputs plus n layers. Maybe. Super dot net. We don't need that myDense layer self in super, do we? Let's have a look. Python class definition. Super. Let's just keep going. And then build. Where you can do the forward computation. Okay. Beautiful, and they build a ResNet block there. I'm going to get up hands-on machine learning. We're reading through this the other day. Hide notebook. I want I think it's 395. Here we go. Yeah, so this is how they make a residual block. Yeah, that's what I'm talking about. I'm going to copy this, make it quite similar. M layers and neurons, and then quarks, init with keyword args, self dot hidden. So this is going to be French Toast Mafia. Hey, what's going on? So we need some skip connections here. Or do we? Let's triple window it. Okay. So we want to build this. So what does our hidden layer have to be? It has to be a fully connected stack which has two outputs. So we want a list of tf keras dot layers dot dense, and we want n neurons in each of them, and activation. What do they use as the activation? I think it's ReLU. Yeah. The fully connected layer is a standard fully connected layer with ReLU non-linearities. So activation can be ReLU. And I think that's it. Yep. There. And this is going to be for in range and layers. Okay. So this is that part, but then we need a call method, because if we have a look here, the call method in a customary layer is where you define the forward computation. So let's define this. Def call self inputs, yeah, then we need to figure out what forward computation we're doing here. Backcast to forecast. Let's read this. Okay. What is theta? Produces the forward and backward predictors of expansion coefficients. So we need, why is it output it to two different fully connected layers? Okay, so I want backcast forwardcast equals Equals something. But for layer in self.hidden, backcast, forwardcast, oh no. Could I do theta? What could theta be here? Theta could be inputs. I'm not sure. So it converges into two more fully connected layers. Let's have a look here actually. Okay, so the theta forwardcast equals linear. So would we have theta f equals TF carriers? Okay. So let's create a vector here. X equals inputs, and then for layer in self.hidden. Update X. And now we have X, but we want, so that's X is now going to be the output of a fully connected layer. But now we want theta forward and theta B forward TF carriers activation. Is there a linear? Linear. So I think we've got okay. I think we've done that. We've rebuilt that linear. But now there's something here. Where does G equal? And then we have a stack input. I think we've just built that. Okay, so the operation for the first part of the ELF block is described as the following equations. So I think that's what we've got here. Stack of and then this is the linear activations of the outputs of the stack of fully connected layers, okay? The fully connected layer is a standard fully connected with ReLU nonlinearity, so that's why we have ReLU here. The second part of the network maps expansion coefficients to outputs via basis layers. Y hat okay. Yeah, we've got that. We've got that here, Antonio. Linear is a layer with one neuron, one linear activation. So we don't need it to return those two. We need to do something here with theta. Here, V forward and VF are forward and backcast basis vectors. So sum over theta okay, so we need YL and XL. So we need to build this. So does it actually take the inputs? We need to let it know what the inputs and the back looking is. Okay, so the out block output X hat, Y hat. This is the back cast. That's the forward cast. Okay, we need to figure out what our inputs are to the model. the very first block in the model. Its respected XL is the overall model input. A history of look back window. We set the length of input window to a multiple of the forecast horizon. So maybe we have that as a forecast horizon. So we need to know the forecast horizon, and what is the backcast? From 2H to 7H. Okay, so we need a backcast. What's the PEP8 for? Who knows the PEP8 for Python classes? PEP8 docstring classes. Horizon equals but that function is only the activation. I think it returns the same input shape. Is that correct? Oh, so you're saying this is better? No, that's incorrect. That should be correct. Is that what you're talking about, Antonio? Where were we? Horizon equals forecast. Two H to 7H. Now we need to make x hat and y hat. Thank you, Antonio. The first part is a fully connected network that produces the forward. So I think the theta this is going to be on the forward horizon. Which if we index because this is going to be the same value here, right? Okay, well, it's still a linear pass. They take the same input. Okay, so right now, theta, before the next step, theta backward and theta forward are the same thing. So the next step is where we change them. So I'm not quite sure how these two differ for now, because they're going to output the same value unless this little denomination here means we bring in the forecast horizon as well as the setup range. The second part consists of the backward G BL its operation is described by the following equations. So y hat, in this call, do I want to produce y hat? So let's x hat theta f will be the forward cast. What is V? Backcast and forwardcast bias vectors. Concrete examples are discussed in 3. Stockliner, what's good? Okay, so the output okay. So if we build the generic architecture, okay, let's see how close we are to M beats. I think there's a GitHub. So this is in Pytorch. Antonio, have a great day. Thank you for tuning in. Okay. We're pretty close to this. Of course, what's some advice that you'd like to hear? Stock learner was thinking of starting stream content related to medicine, such as reading medical themed journals. Do you think this would be a good niche to explore on Twitch? I'm probably not the best person to answer that because I don't know anything much. Well, I do. So I know some things about medical journals, but not much. I would say that is very hard to predict whether it'll be good or not. I'd try it out and see how you go. You'll never know unless you try. All right, so we're trying to just, this looks like they're just using a, we want y hat to be, I think that's our block. What do you think? layer size. Now we want to craft the algorithm. Now we want to stack up the blocks. So now that we've got a block layer, block input, we want to create a stack input. So let's go back to our hands-on machine learning. So we need to create, so the blocks is going to be so class what's the residuals? This is going to be tfcarers.model, and then if we go here, it's going to take blocks, Now let's combine them. What is happening here? So they make a copy of the data. Okay, so this is going to take in the tuple of the output of this. So that'll be Is that correct? And then we go down here. So the stacks are just Noel Maxwell asks, can I give a quick recap of what we're doing? We're replicating this architecture, which is the n-beats algorithm for time series forecasting. We've got some data here that we're trying to forecast on, and this is one of the best performing algorithms for deep learning, M3 and M4. They demonstrate two state-of-the-art configurations for n-beats, improving the forecast accuracy by 11%. So that's where we're up to. And we're currently defining our architecture here. So, yeah, we've got this is the block layer here. Right, so that's the block input. And now we're using the block input to create stacks. So we have a minus here and a plus here. Let's see where the stack input. So XL previous block removes the portion of the signal. So they get the residuals. Not sure what the input mask is doing. Okay. Residuals, input mask. We currently don't know what these are. Forecast equals forecast Not sure where both of these come from. To me, it looks like they come as the output of that. So this is going to be outputting the backcast and the forecast. That actually makes a lot more sense. Back, forward. Let's figure out what this flip equation is doing. How do we create a tensor? What is happening here? I don't know why Chrome has gone bongos. So they then flip X they flip the dimension here. So they flip it. So this will be the backcast. That gets flipped. And then the forecast also gets flipped. Then X Okay, so they flip the residuals and the input mask. Not sure why. So this is just creating the model. Let's have a look at trainer. Oh, what does this notebook tell us? Let's have a look at the make file. So if we make run, all right, let's have a look at build. Sorry, main.py. Oh, this just builds the data sets, doesn't it? Okay, so we're pretty deep here, but this is good. So let's keep digging. So we've got the output of the blocks, y hat, x hat. Let's keep reading. If we just take it off face value in this stack, what happens? Stack input, I'd like to know what this is. So what is this minus? So the block, that is the residuals. Is this mentioned in the paper somewhere? The backcast residual branch, XL. I'm wondering why they flip the residuals. The final forecast is a sum of all partial forecasts. Yo, what up? I am VAZU. So forecast is the last. Maybe these are the residuals. Minus the backcast. What is the input mask? So this is definitely, is there mask here? Today we are working on replicating the NBeats paper. Which is really good for univariate time series. We focus on solving the univariate time series point forecasting problem using deep learning. And I have some arbitrary time series here. And we're trying to improve upon it using the NBeats algorithm, which can be seen here. This is what we're trying to build now. But I'm getting a little confused with what we're doing here with the paper. No, the flip reverses, makes a copy of a tensor and then flips it. So it reverses the order of the tensor. But I'm not quite sure why we would be doing that. At least that's in their model code. Okay, so the target and history points that fall outside of these time series limits, given the anchor position, are filled with zeros and masked during training. So n beats, this takes as input blocks. So I'm guessing this is X, the back cast, and then the forward cast. So maybe that's why they flip. So that returns a tuple, what we've got here. But I'm still very confused as why they create residuals. But this makes sense if the n beads class takes in blocks, where do both of these come from? So I'd like to know where the generic model gets created. I think the clue might be in the make file. Dataset. Yeah, so this requires a Docker image to run. Okay, in experiments, let's have a look in here. Okay, here we have the inputs to our models. Okay, here we go. We've got an X and an X mask. X mask. Now let's figure out how these are created. Okay, we're getting somewhere here. This creates windows. So it creates zeros. Wonder what this would look like if we just passed it a time series. Because this doesn't look like it relies on any methods. And that's the input to our model here. Just going to hack around with this function here and see what it does. Do we have NumPy? We should have NumPy. No, we need to fix the input here. When we imported our data, what did that look like? So it's expecting a matrix. MP array. So we can just do df values. Oh, this is interesting. What's smile direct plum? Far out. Google. Do you want to? So this is expecting it in the shape of time series time steps. What is happening here? Google Chrome. Let's have a look at this ML engineer position. So these people help people get a great smile. And what are they looking for an ML engineer to do? You will fit right in if you take joy in seeing your work in production. 5 to 10 years, what will you actually be doing? 3D data. They want a machine learning engineer with 5 to 10 years experience. Okay, Shaking Basket says exchange first and second column using pandas using permute method, then pass these as NP values. So is permute pandas? Or I think that's NumPy, isn't it? Where are you talking about the permute method? So this is saying that it's inspecting time series time steps. So this wants time series, time steps. So this is my time series, and this is the time steps. So let's get D1 new. Now, why is that turning? Oh, so this wants a list of time series data. So it's turning it into a list. Okay. So this is a list of time series. What if I only have one time series? So, okay, so their input data is multiple time series. So they're forecasting multiple time series at a time. I just want one. Okay, so let's write a little note here. All right, I'll be back in a sec. All right, so the confusion here has become that they ran their time series model on multiple different time series. So now let's see what would happen if we just had... The trick is here. So what does the block expect? Nick one. I'm not sure. I'll just keep streaming until I get bored. Why is that? I don't really have a time limit. Maybe another hour or so. I'm really trying to figure out what this is. I think this is overcomplicating it. Residuals minus backcast. So if we come a look, let's compare this to the actual formula. That'll probably be a good comparison. Okay, so XL, I believe that this is this. Residuals minus backcast. Because the backwards cast is going to be theta oh. Raid. This is the first time I've been raided. Hello everyone. Nice to meet you. Thank you, Nick. Hello, everyone. If you're just joining in, we are replicating the NBeats algorithm. So this fully connected neural network from this paper for time series data. We're in a little bit of a hurdle at the moment. We've got some code over here, creating an NBeats layer block. This is hopefully similar to what they've got going on here. I'm pretty sure it's the same. Now we're up to stacking our inputs, but after diving into the original code GitHub, which is in Pytorch, by the way, this is in TensorFlow, I'm a little confused with a few of the steps they're doing. Mind you, the paper was set up to run on large scale, like lots of data sets, so they were doing like 10,000 experiments at once. I just want it to work for a single time series data set, which is very arbitrary. So that is what I'm trying to do at the moment, replicating this paper for my own custom data set. And I'm not sure, we were comparing the math of this versus the code. So the proposed architecture has two residual branches running over the backcast prediction of each layer and one running over the forecast. So XL, that's the backcast. So this is the residuals. XL is what they're calling the residuals. And the forecast here is just the sum of Y hats. So that's the forecast there. But they flipped X for some reason. And we figured out what X is. My background is really noisy. What can you hear in my background? Cars? There's a street right there. Or is there a fan or something like that? Maybe that's my computer going off. I'm surprised at how much my microphone picks up the cars. If you have ideas of how to fix that aren't closing the window because otherwise it would be too hot, I'm all ears. The backcast residual branch XL can be thought as running a sequential analysis of the input signal. Previous block removes the portion of the signal X, so the backcast minus 1 More importantly, each block outputs a partial forecast, Y hat. Okay, so this is where I think what we've got here. So this might be the partial forecast, which is just the last time step. They're calling that a partial forecast? Is this the partial forecast? And then forecast equals forecast plus forecast. Full forecast? So that's Y hat here. I'm pretty sure. So Y hat. The final forecast Y hat is the sum of all partial forecasts. So this is the block forecast. Add those together. All right, let's dive a little bit deeper into this. Who knows what the triple line symbol is? For all other blocks. Ashik, what's good, my friend? How are you? Apparently I can use noise gate as a filter in OBS. Thank you, 7. X flip dims. So they take in a whole time series. Where's the pre-processing function? Here. Build forecast. X mask. I don't want to mask anything. So how about we just can this, X equals that, and then maybe I won't have a mask at all, but I will make residuals here. X equals reverse. Axis equals dims. So TF reverse. Let's just see what this does. TF reverse X axis, or is it axis or dims? I just looked that up. Yeah, tensors. Axis. Input mask that can get bounced. Forecast, I'm guessing that's the partial forecast. I'm going to call it that. Partial forecast. They don't even use I in here, so they have I in enumerate. They don't use I. I'm going to call this X hat. Y hat. Block on the residuals, pass the residuals through that, through our block. We don't even use the residual. It doesn't return the residuals. Derp. Oh, well, no, it's updating it. Residuals equals residuals minus backcast. Don't know about that. And then the forecast equals the partial forecast plus Y hat. Return forecast. So the residuals is what goes into our block, which is up here. Now, ideally, this should be times an input mask. Well, according to the original code. Which we will trust them because they are the authors of the paper. But have we got this? Let's bring this back over to there. So the residuals is what I'm guessing is this. Because if we come back up here, is this what we're doing? We have a stack input which is x here. Then we have a block, which is, our block is this. And then there's some sort of minus here. So I'm guessing that this is this. Ah, so the residuals is the look back. Look back period, I'm guessing. Because that's where the minus symbol comes in. Minus. And the stack forecast is here. That's the addition. Okay, let's try get this working for our data set. Yeah, where does the horizon come in? That's the y hat. All right, let's try to run this with some data and see if we can get it to work. Make model, we want this is where we might run into some trouble. What is theta? Outsize, theta size. So what do they want to define as theta size? N beats, and we want n beats block layer. Now, how many stacks do we want? What parameters do we need in this? What's your exam, Ashik? Oh, what does our model look like? Microprocessors and microcontrollers. That sounds cool. We want to input shape a sequence. Okay, we're getting something wrong here. Okay, let's have a look. Peace out, Quang. Thank you for tuning in. So what's the in sample size? Now, let's have a look at the hyperparameters that they used. Okay, so this is why they reproduce their architecture. Serene Master, what's going on, my friend? Deep learning is BS. It's all fake. How could you possibly understand the math here? It's all matrix multiplication. That's all it is. Atom optimizer with the default settings, while optimizing the ensemble members, relying on a minimization of the S-MAP metric. Let's find the appendix. Okay, so if they build a stack of 5 layers, so we start our study with a generic architecture that consists of stacks of one residual block of 5 fully connected layers. This, and then thank you, Ashik. I was going to ban that person anyway. So they do n layers 5. Well, it's actually going to be 4 because there'll be 4 layers in here plus this layer. And stacks Ah, I see. So this is where we combine the partial forecast. Now we have a small forecast here. But okay, so this is where the input mask comes in. Okay. I'd really like to get this running, or at least just try to get it running. What do we need to do? We need to define theta. What's our horizon? We'll have a backcast size of 7. So it'll look at 7 time steps at a time, and it will predict 1 at a time. Now let's find out what theta size is. Now the generic Now the input size is going to be look back times the horizon. And the input size is going to be look back times horizon. So let's dive into here. When they create a layer, what layer size are they using? Now they use gen here. Where's the gen file? Here we go. These are the parameters that they use. Five 12. So let's go here. Look back equals 10 steps for daily. And then layer size. We're making some progress here, team. This is very, very exciting. And then n layers is going to be 4, and then n stacks equals 30. Okay, and then the horizon was, we found that before. That was in D. So are you trying to predict 14 steps ahead? "14 steps ahead" based on what? when we imported our data set, okay, so the horizon is 14. We want to predict 14 steps into the future. But how many time steps do we look at? Oh, it's a look back times the horizon. Where does the look back come from? I want to know where the look back comes from. Where instance gets defined. So if we come back, I wish it would tell us what look back is. Is this up here? Look back period. Boom. Okay. How long have we been going for? Just over 3 hours. All right, so we've got some fairly good process here, I think, or progress with replicating the NBeats model. We haven't got it running yet, but we had to kind of deconstruct a couple of things that they were doing. Tomorrow we'll probably backstep through the code and make sure it lines up with the model. And then we will try to get it running. So let's write that down next. To do step back through model, make sure it lines up with paper, make model as generic as possible, and we want it to work for a single time series only, not many experiments, like the paper. Get model running with toy data set above. Okay, so that'll be our next steps. Let me just go here. I just want to look up one thing. Torch linear. Okay. I'll be back tomorrow. Thank you all so much for tuning in. This was a blast. Thank you to Nick One Data Science for rating this channel. Hope you all enjoyed the stream. As always, keep learning, keep moving, and I'll see you next time.